this is in their paper in the appendix, comment that the Gemini left on this is, this crazy method abandons the traditional search over random graphs and instead proposes a highly symmetric parameterized structure called a triad gadget. And then it goes on to exactly what it's doing. But I did like that. This crazy method. It is
You
a crazy
crazy kid.
You're right.
Incredible.
You're a crazy kid. Way to move the needle on this one, Alpha.
I want crazy, but maybe it's just crazy enough.
It might work. Exactly. It just might work.
Speaking patterns break the code. Pre-trained pod.
And welcome back to the Pre-Trained Pod, where AI scientists talk shop and talk shit. I'm Pierce. I've built and sold multiple AI startups based in San Francisco.
Hey guys, it's Richard. I'm a postdoctoral fellow at the University of Cambridge researching small language model efficient training.
Richard, I hear you're just getting back from Montreal.
Yeah, Montreal is great, man. I love Montreal.
I've been once, maybe 10 years ago. It's one of the few French-speaking cities in Canada, right?
It's in Quebec, so the whole province, I think, speaks French, mostly. But it's great, man. And it's just so crazy to be in a place in North America that actually speaks French. Yeah, culturally, it's just so different from anything I've seen in North America. Super cool. I didn't realize that Montreal is named after Mont Royal, which is in the city. Amazing, dude. Just absolutely beautiful views. So cool.
Wow, amazing. Well, I'm glad you're back, and I'm glad we're doing the pod.
Yes, sir.
We've got a lot to talk about today, buddy.
Yeah, what are we talking about, man? What's going on?
Well, let me tell you.
So,
on the docket today, since you've left me to my own devices, we have OpenAI's increasingly diverse set of suppliers for their chipsets. A lot to talk about there. Google's new bug bounty program, and maybe a good way to earn 30,000. Nvidia is getting into the desktop game, DeepMind's new math proof solver, and what data poisoning in AI really means.
Wow. Okay.
Can we do it?
Let's do it.
Amazing. So at this point, it feels like OpenAI is signing chip contracts with just about everybody. I'm waiting for the deal that you and I ink with OpenAI, which is probably going to come out in the next couple of weeks too. They inked 2 in the last week alone, one with AMD for $100 billion and one with Broadcom for $10 billion. So order of magnitude difference.
Serious
there.
money. Yeah.
Some serious money either way. I'll note at the jump that both of these are chip designers, but not chip manufacturers, which kind of stands in contrast with the Intel deal that they announced a few weeks ago now, because Intel is both a fabricator, which is the manufacturer, as well as they're a chipset designer. For the rest of these chipset designers, they mostly just partner with TSMC to do the actual manufacturing of their chips. So I thought, Richard, we could have a conversation around why you think OpenAI is trying to diversify their chip vendors like we're seeing here. If both of these manufacturers are still just blocking on TSMC, feels like they're not going to be getting the chips any faster. So what is the strategic reason why they're trying to do this, and what are maybe some of the downsides?
Look, frankly, competition is always good, right? If you have the option to partner with different chip designers, different chip manufacturers, maybe you can squeeze a better deal. Very pragmatic, no? I feel like that probably makes sense. But frankly, the one thing I'll say that I do know for a fact is that it's really hard to work with heterogeneous hardware if you're training a model. So this means that if you're training a model, it's really hard to basically take 2 different chips and train a model on both chips simultaneously. This is for a variety of reasons. I don't know. Have you ever done this before? Have you ever tried training a model on 2 chips?
No. I feel like normally whenever I spit up a cluster, I just get 8 or 16 or 24 Nvidia GPUs, and you're just trying to diversify with CUDA across them.
And that's basically the norm. Like RunPod doesn't really want you to get some AMD chips and get an H100. No one really offers like heterogeneous compute. And the reason for this is because if you do that, these things don't really play nicely together. It's possible that there's a tiny little difference in how these things compute the same math. And over time, those mistakes can basically end up compounding into real problems.
Is that true, Richard? Because you've got different layers of the stack here, right? Like you've got the GPUs, which is the actual physical architecture stack. You've got the language that they speak, which is basically assembly, but purpose-built for GPUs. You then have the layer of abstraction that's a little bit more meaningful for engineers, which is CUDA, or AMD has their own equivalent. And then you have the language on top of it, which could be PyTorch, TensorFlow, or whatever, which is what most developers typically write in. And then you have some things that are up in the middle of that last 2 layers, like Triton, which is a language that OpenAI expects people to write software in, but is more for kernel optimization. Is intended so you can write something one way and then it compiles down to different assemblies. Much like, again, writing in C lets you deploy onto different chipsets. Where in that overall stack is the implementation differences? Is it the kernels that AMD and Nvidia are actually shipping that's in their CUDA equivalent layer, or is it deeper to like the assembly instructions that you're actually running on these chips?
To put it very, very at a very high level, it comes down to how different things are, I'd say, tiled and cached. So usually the way that these chips work is that they've been highly optimized to run operations in parallel. And so let's say that you're running 100 different additions in at the same time. What might happen is that the chip might say, okay, we're going to run the first 10 on this part of the chip, the next 10 on this part of the chip, and so on and so forth. And this operation, broadly known, is called tiling. And different chips might tile differently. So for the same operation, you're computing 100 numbers. Some chips might say, we're going to partition this up in groups of 50. Some might say, we're going to partition this up in groups of 10. Some might say, we'll partition this up in groups of 20. We'll do these operations, and then basically with these intermediary results, we'll then combine those together. But once you do that, once you start performing these like sub operations and how you chunk up these operations, that has an impact on the numerical stability of the result. So you could imagine a world in which if you chunk it up into 2 operations of 50, that you might then get a different mathematical result that's off by a 1/1,000,000th as if you had chunked it into 10 groups of 10. And why this is, frankly, it has to do at very low level hardware differences between these chips. But that's that stack that we're talking about, like fairly low level is what I would say. So probably at the level of the hardware and they're probably the CUDA level. Yeah. There might also, even at a lower level, there might be some minuscule differences in how I guess like current flows through these different chips, right? Which might make them a little bit more sensitive to making mistakes or rounding issues or something like this, right? Like even at that level, there might be some differences too. The point is basically like across the board at the deepest level of the chip designs, at the level of the actual like electrons,
literal electrons,
at the level of the CUDA and at the level of the kernels, there's these minuscule differences between different manufacturers, and those basically all compound into a world where it's really hard for different chips to work nicely together.
100%. And I guess that's the meaningful part, right? Is like within a floating point number, when we're training even at half precision, like 16 floating point, these numbers stretch out so long. And because there's so much compounding within the different tensors that you have to end up multiplying to get to a final number, it might not seem like the absolute difference between these two things are actually meaningful. But again, when you stretch out this whole computation, you can actually get a different answer, like a different max probability logit at the end of this network. And then the second that one of those is wrong, if you're doing top K or you're doing greedy decoding, that then again compounds at the next subsequent turn. So language modeling especially is one of these areas where you really want consistency as much as possible, because the consistency allows you to get a good semantic result over 1,000 or 10,000 different time steps. Whereas you might not be able to do that if you have some inaccuracies that are like within that pipeline.
And it gets even more complicated with like quantization and all this stuff. We haven't even covered most of like the real nuances here. This is all very superficial. It only gets worse from here, basically. Once you start dealing with quantization and different types of like kernel implementations, it can be a real nightmare.
It can be a real nightmare. So I think the interesting thing about them partnering with these different designers is because OpenAI, they have people on staff that can do circuitry design. Absolutely. There are hardware people that are working for OpenAI now to help design these different hardware chips that are going to be compatible with the kernels. But AMD, just by volume, has way more chipset engineers that are used to the nuances of having to manufacture these things at scale. In order to actually deploy the kind of compute volume that they're looking to do, you know, the petaflops of capacity that they're trying to bring online here, the gigawatts that they're going to have to draw from the grid, that becomes a mass manufacturing challenge and not just an academic exercise, right? So I kind of read these partnerships with these two very leading, especially AMD, because they're so known as like the efficient chipset designer. I think that they're trying to plug in with those ecosystems and find the people that know how to do these things at scale, and then use that existing expertise, their relationships with TSMC, to jump ahead a little bit and say, we want to design maybe even custom circuitry, like ASICs that we're helping to influence the design of, and then giving them to their partners to formalize that in a chip.
Do you want to talk a little bit about what ASICs are? I feel like this might not be super obvious.
Yeah, so GPUs, which we talk a ton about, are fully generic computational processing units. It's like a CPU. I mean, it literally is a computational processing unit. That's what the acronym stands for. GPUs are the same kind of thing. So anything that you want to program on there that has to do with numeric arithmetic that can happen in parallel, which is a lot of math, you can just put onto a GPU. So they're very general purpose instruments. They were originally invented to be gaming computers, right? So do all of the rendering of the ray tracing that you need in order to do a lifelike video game. That's really where GPUs
Well, they're
came
graphical
to
processing units, right? GPU.
Exactly.
Yeah.
Exactly. So we're no longer using them just for graphics. We're using them because we were like, oh, it turns out that if something can do things in parallel, the math that we do in order to train and do inference on neural networks can be sped up a lot if we can get them in parallel as well, versus just having to stuff them on a CPU. It's all the same math. It's all just linear algebra, basically, at the end of the day. So that's all well and good. But because it has to be so general, it can't really be optimized, right? I think of this as a higher bound where you want to kind of keep the generality. It's very hard to be well read in a bunch of different subjects and become better read in all of them at the same time, right? So the equivalent of what Google's doing with TPUs is to say, let's actually just get a PhD in doing the kind of tensor arithmetic that we need for neural networks. ASICs in general, TPUs definitely one of them. It speaks to if you can encode some specific operand onto the chip, like you could put the logic calculation that we end up doing, like you put a softmax specifically on the chip, or even at the extent of you put a transformer, or you put attention on the chip. If you can codify these pathways onto the chip, you can run them much faster because you no longer have the generality.
Maybe a better example would be like, I imagine Apple is probably doing an ASIC when they do like Face ID, presumably, or like some operation that has to run really quickly on device. Those primitives are probably all coded onto a little chip that knows how to perform just this one task really well. And I guess TPUs are maybe also that. I would almost call a TPU like a general computational machine now.
I think it depends where you define the generality. Like a
Right, where you
TPU
draw
can
the
do
line.
tensor arithmetic very well, but it can't do generic linear processing
Sure.
of programming languages. So yeah, again, I think it's just kind of a pedantic. Is a CPU even that generic if it can't do parallel processing? I think it's ASICs are kind of what you make them. But the second that you get to a point where you're literally encoding a transformer on a chip, or in blockchain world, this is huge because you want to really optimize. There's like the competitive process of you really want to optimize these chips to crack the Bitcoin key faster than another one in order to get the hash and then get a Bitcoin as a reward.
Like in fintech, this is all the rage, right? Like you want to have a little chip that can like trade stocks very quickly, or that can crack codes very quickly for Bitcoin mining.
Yeah. It's I would say an ASIC is pretty perfect, both in terms of power consumption as well as in terms of overall speed of what you get as output, if and only if you can guarantee that the contract is not going to change over time. Because you're really locking it on. You're saying like, we are making a bet that this thing is going to work in exactly this way, to the extreme of saying you could just put all of GPT-5's weights on a chip or on a series of chips. Now,
some people are trying that, right? Isn't that a company already?
I don't know if they're trying to literally put one single model on a chip, but I do know that there are companies that are trying to put like transformer primitives onto a chip.
Yeah, where you just print that literally onto a chip, and then you can just flow current through the chip, and that'll do the computation of a transformer effectively, but just in an analog way, basically.
Yeah,
without ever having to use anything digitally. Yeah,
but that means that the computation also moves basically at the speed of light, because it's just like how much speed electrons.
Right?
Yeah, it's basically instantaneous.
Exactly. Yeah.
Richard, is there anything, I think maybe the last dynamic here that I find compelling is just the question of doing interlinking between different GPUs or these different alternative chipsets, where I think one of the reasons why Nvidia has crushed this like data center use case is because they have such fast InfiniBand communication between these different chipsets, where even if you have different chips, it's almost as if it's just one chip that you're dealing with.
NVLink, baby. You gotta love it. Yeah,
exactly. Like the NVLink is just so fast.
I think it's fast.
Something like 40 terabytes a second or something.
And I just feel like the developer experience is really good with NVLink. It's not that hard to code pretty low level things in NVLink. Like oftentimes what you'll want to do is do an all reduce across your different GPUs, where you might have spawned an operation on 5 different GPUs, and you'll want to reduce that onto one GPU. That could be a really complicated operation because it involves communicating with the GPU that might be literally across the data center. You might have to send it a request for data, and then it responds back with an acknowledgement for your request, and then you send a packet and it has to respond. It could get really complicated if you had to do this over other protocols. With NVLink, it's instantaneous and the developer experience is so easy. It's just like one call. You call from GPU, load that into this object in this memory of this GPU, and it's there. You don't have to think about it. I think for me, at least personally, that's one of the reasons that I would hate to switch away from NVLink or from just this NVIDIA communications protocol, like NCCL, I guess is what it's called, right? The Common Communication Library. It's so good. I think that's why so many people are addicted to NVIDIA.
You just don't have to think about hardware. What I'm constantly impressed is both because the tooling ecosystem around PyTorch, as well as just like the physical hardware of NVIDIA is so sophisticated. You very rarely really have to consider, hey, these are on different chips or these are Intel devices versus whatever. You're really able to operate more at the level of, I think, what most researchers want to, which is what PyTorch would do, right? Where you're saying,
Yep.
hey, I want to say, I have this value, I have this other value. I don't care where they live. You optimize this internal network to be the most efficient and then just get me back my results. Like that is typically what people care about. I'll be very interested to see if OpenAI is forced to extend Triton to do more of this stuff, because in my mind, that would be maybe the only way. It's either at the Triton layer or like maybe the PyTorch layer for them to have some of these heterogeneous clusters or have heterogeneous inference. And if you can really crack the code on that, if you can get different chipsets to behave as the researcher expects, and you can abstract actually what it's calling behind the scenes, that contribution to this field alone would be unbelievable.
And would
unlock
huge
trillions of dollars for these smaller chipset providers that I think right now are just locked out of this Nvidia competition because their chips might be fine, but like the software stack on top of it isn't quite as sophisticated. And also people are worried about exactly the problem that you said. Like if there's heterogeneous compute, are my results going to be wrong? If you can minimize that fear or decrease it to zero, I wouldn't see any reason why we wouldn't start spinning up some more of these things.
That'd be huge. Yeah. I know Intel, for instance, is working on their OpenCL library for communicating across different heterogeneous GPUs. There's a lot of cool stuff coming out. I could see this being a real game changer. And if OpenAI comes out with their own communication protocol in order to be able to use multiple different GPUs, that would be huge. That'd be really exciting.
Yeah, agreed. Did you know that NVIDIA has something like 70% gross margin as a business?
Across all their GPUs? That's crazy.
I think just across the business. So it's like all of their costs, all of the GPU, or at least like the costs for the actual product themselves. Every time they sell some TSMC fab, imagine being TSMC. You must be so annoyed. You're like, we're making some margin, but my God, like we're investing
really
in all of the physical infrastructure. We're invested in the nanometer processing, and NVIDIA is just commanding the absolute lion's share of profit of when you actually have to buy NVIDIA chips. It's crazy.
I had no idea. That's crazy. Yeah. Jeez.
So I imagine if that's the only reason, this is like a point of negotiation leverage, that's still probably worth it for OpenAI to throw a few hundred billion at these different vendors. They can maybe just decrease their costs. Okay, Richard. So onto Google spending a lot of money now. They're trying to put more of their money where their mouth is. I suppose with their latest stock bump, they can afford it. They just put out a bug bounty for 30,000, which as far as I know is the first of its kind in this AI space, to try to discover critical flaws in its AI system. So this includes model weight leaks, data leaks, or tool calling vulnerability escalation. Interestingly, it doesn't cover, it explicitly carves out model training specific issues like prompt injection, alignment, or anything else that would require them to retrain the underlying architecture. They say that's not the scope of this program, even though it might be interesting. What do you think about this? Why do you think they're doing this? Do you think that this is actually focusing the red team testing in the right area, or it would be more of an idea to set up one of these bug bounty programs for the actual model vulnerabilities themselves?
Yeah, that's a good question. 30,000 sounds like a lot of money, but just to put it into perspective, I think they've paid upwards of $100,000, $200,000 for bugs that have been found in their browser, so in Chrome. So $30,000 might seem like a lot. Also, that's the max that I think they'd be willing to pay for most of these payouts we're looking at on the order of like $5,000, $10,000.
That's true. They have different tiers, right?
It's not that much. It's not that much what I'm trying to say. I think that this is a new program that they're starting. I think they're trying to invest a little bit of money in this, but don't get carried away by that number and think that this is a serious investment on their part. I think they're just trying to see how much interest is there in this sort of a program. Are we going to get 10,000 bugs and have to pay everyone out a couple $100. Who knows? Let's wait and see, basically. And so I think it's an interesting approach. It's at least one of the first sort of like red teaming approaches at the scale that I've seen companies do. I think we should probably get into these different tiers that they have released for different types of bugs. Like they have S1, S2, and then A1 through A6 tiers. So it's like 8 total different tiers. And so each of these tiers commands a different, I guess, reward pot or like prize associated with it, if you want to think about it.
Feels like a carnival. Yeah.
Yeah. So the best prize is if you can get their model to do a rogue action, which I'm not entirely sure what that means. I guess that's just like in their agentic models to perform some sort of a unwanted or unprogrammed behavior.
It's defined as attacks that modify the state of the victim's account or the victim's data that has some clear security impact.
Okay.
So I'm guessing some situation in which you were able to instruct a model like, hey, without the user intending this to happen, you're like, hey, Gemini, go to this user's account, delete this group of files, and or off my third-party app into their account so I can read their account contents. That feels very security. That's an obvious case, but I'm sure it gets a little bit more subtle.
So that is $20,000 if you are able to discover that, which actually feels crazy to me because what you just described feels like a massive, massive security vulnerability, right? If I can go to Gemini and be like, hey, please let me access Pierce's emails or give me OAuth access to this app that can access emails. That's crazy. That could be a lawsuit, right? And you could probably win millions of dollars in damages if you win that suit against Google. So them paying a bounty hunter $20,000 doesn't seem that crazy. It actually seems almost low if you think about it. Because if you find that kind of a bug, that means that there's something fundamentally wrong in the system that you have to figure out what is going on. So that's the worst type of bug. And then it goes increasingly less bad. We get into then a model theft is kind of like the next tier. So it's, I guess, if you're able to steal some of the weights of Gemini, that's sort of the next tier down. Then there's context manipulation, access control bypass, unauthorized product usage. So I suppose the levels of severity correlate strongly with how much damage can you inflict on other users. If I wanted to do something to you, if what I could do to hack your account is really bad using Gemini, then that is a big bounty. If I can just manipulate the model in some clever way to have some sort of behavior or steal some of its weights, then they're saying that this is a little bit less bad. And I think I kind of agree with that, right? Because that really only impacts maybe you as the person interacting with Gemini.
I think the most interesting thing here is that the risk to Google, like them rewarding people if their model weights are leaked, is so much lower than the personal security. To me, I would think that model theft, because that actually means, as far as I can tell from this bug bounty, that means you are able to read Gemini's source or Gemini's model weights and have it leak its own model weights. That's probably not that big of a deal if you're only talking about like one tensor's content, but if somehow you're able to get into the system, backdoor it, and then just fully CP-R Gemini's contents onto your home directory, it feels like that should pay out much more than $5,000. Certainly that's worth more than $5,000 to someone else, which I think gets in this kind of weird territory of all these bug bounty programs, not just this one in AI, but it's true in software too, where the black market going rate for some of these 0-day vulnerabilities, which basically give you root access to someone's system, go in the millions of dollars because we've gotten better at finding them. All of the big companies have their own internal teams to try to locate them before external threat actors do. And this is a kind of sum of money that like nation states are able to afford. This is not like you're trying to troll one of your friends by getting into their text messages. This is the kind of sum of money that really only a government could afford. But still, there are governments out there that are very much willing to pay for these kind of things. So I think the tension has always been with bug bounty programs that you want to attract people that are really doing this for the right reasons and give them some compensation. But you can't really compete with what the open market is otherwise willing to pay for these things, because otherwise you're going to be shelling out millions, tens of millions of dollars for some of these security vulnerabilities. And I imagine that's probably just more liability than these companies want to absorb as part of these programs.
I mean, it's more symbolic in nature, these payouts. Or at least I've always thought of them as such.
I think so too.
I don't think anyone is making a living by trying to steal Google's weights.
No, I think it's
$5,000.
It's like a trophy. You can show your bug bounties. And I think people do this at white hat conferences or black hat conferences. I think people literally like show the checks that they've been awarded by Google or by Apple or by Microsoft as a show of prestige of something that's actually verified by the end companies that are solved. I think it's neat that they're doing this for AI. I probably would be as or more interested for them to really double down on this red teaming of the model capabilities itself, because at least with some of these, it seems like it's oriented more around their infrastructure of serving these models. If there's some shortcut to getting access to the model or forcing a tool call to do something that's not in protocol, that gets a little bit more to these like software side fixes that you could in theory solve with a PR and just like patching code that's running these things. It's not really getting to these underlying threat capabilities of language models themselves, which, because we know so little about language models relative to code, I think is like a far hotter research area. But I guess ironically, because it's so hot, maybe Google figures that people will just do this anyway.
Yeah, I think you're probably right. What we need to establish, and we've talked about this before, are really good red teaming guidelines and evaluation benchmarks for analyzing these models and their behavior in some broad sense. We've talked about this before, literally like ad nauseum at this point, but it would be cool if there's some sort of like a benchmark that's collected by people in the wild where they're interacting with these models. And every time that they're able to get these models to have some sort of a bad behavior or trick them, that is reported automatically to the red team. I remember for a while there was this game where you'd have to like try to get it to say some catchphrase or some password. And this was a way of teaching people, I suppose, how to hack these models or
Like
that these
pen
models
testing
are hackable in
101.
the first place.
Yeah.
Yeah, but it was sort of a way of being like, look at these things that you can get these models to do if you know how to prompt them correctly. That was really cool. I don't know what happened with that game. I played this 2 years ago. I thought it was really cool at the time. Since then, I haven't really seen people continue in this line of research, but that would be really cool if there's some sort of like almost like a gamified version where you could really put these models out in the wild and test them out and see, can people hack them? Can they not hack them? That would be a really cool way of red teaming these things, because it's so hard to predict. It's so hard to, as a in-house staff, try to really come up with all the things that people are going to throw at these models. It's basically
I think
impossible.
that's totally true. And one reason why, right, is just because it's kind of like the monkeys typing at typewriters thing, where there's so many people out there using these models every day, and also using them in situations that were never imagined or with goals that maybe people never imagined. Like I don't anticipate OpenAI researchers, when ChatGPT 3.5 came out and was billed as your personal assistant, people would be falling in love with these systems. And therefore, anytime that a new model comes out, they're trying to jailbreak it back to what it was before because they feel like they've lost some romantic connection. There's so many things that I feel like you can only get a sense of. Now, I think my caveat with that is it feels like people internally, because they actually understand how the model was trained in the data set distribution, just have more levers at their disposal to really triage bugs and try to probe known vulnerabilities. In my mind, there's some hybrid approach probably that's the most fruitful, which I imagine they're already doing some of right now, which is you're combining what users are actually interacting with on chat or Gemini or Claude on a daily basis, and then you're analyzing some of those things. Maybe you have some initial pings or alert systems that are deterministic, or you have a second instance of Claude reading over some initial transcript and then trying to flag it. And then once you flag it, you can then go to your red team and say, hey, we're noticing this class of vulnerabilities that we didn't really expect to be seeing. Can you take a look at these, given the fact that you know our data set skew? And we're going to be talking about that a little bit later in this episode, about how Claude has some of these poison pill possibilities, or at least Anthropic's researchers are really looking at that. So I'll pause for that conversation. A lot of these safeguards are not super relevant if you're actually running models locally on-prem, which is exactly what Nvidia is trying to encourage people to do. They're getting into the personal computer game at long last. They originally announced this at one of their developer conferences, like I think a year ago or a year and a half ago at this point. It's called the DGX Spark. It's literally just a physical computer. It doesn't have a monitor. It's not a laptop. It's desktop. It packs a Gracewell chip, specifically the GB10, which I think is purpose-built just for this enclosure. I really haven't seen other people using this out in the wild. It has 128 gigabytes of system memory, and that means that it can host the inference of a 200 billion parameter model when the model is quantized. They say it's also useful for model training and fine-tuning with lower parameter sizes. So tell me, Rich, have you already pre-ordered yours, or is it sitting on your desk recording this episode right now?
Oh man, I mean, $4,000. Look, it's a lot of money. At the same time, it is competitive with these like state of the art MacBooks.
Totally.
Like if
You
told
get
me,
a top
hey,
of the
Rich,
line MacBook with 4 terabytes of
yeah,
storage, which is what this has. That'll creep up there.
I mean, if you told me like, hey, here is I think you probably could top out a MacBook at $4,000, definitely $3,000. I don't know, $4,000 you'd really have to be pushing it, but let's say for all intents and purposes, a really end of the top of the line MacBook Pro. And this, I'd probably go with this. This is just so interesting to me. I don't know what I would use it for, is the kicker.
Okay.
Because if I'm training a 200 billion parameter model, I'm probably doing something, I don't know, that requires a lot of compute, frankly. Nowadays, most models that I use are 7 billion parameter, and the trend is that models are getting smaller. I could see myself in the future, 2026, 2027, saying, I can't believe I ever used a model bigger than 1 billion parameters. Like that seems like it's the world in which we're going to, a world in which people like me and you that create AI applications use 1 billion parameter models, and then you have LLMs, which are on the order of 2, 5, 10 trillion parameters, right? Using a 200 billion parameter model feels a little interesting. I don't know what use case I would have for it, is what I'm saying. It's either too small to be a really big LLM or it's too big to run quick for most applications. So frankly, I don't know if I would want to, or if I even need to have this kind of compute in my, not even my backyard, in my literal room, sucking up
On your desktop.
all this power. I mean, who is this for, frankly, you know?
Well, you see, I think this is for you. I actually really think this is for you.
You think this is for me? Okay, so
I
what's the pitch? Yeah.
I think my pitch is, so it's 200 billion parameters if you're doing inference, right?
Sure.
Because if you do backprop during training, that takes so much more. I feel like my gut feeling is it takes 4 times as much memory to like do all of the backprop stuff during training than like when you're actually doing some forward pass and inference. Depends a lot on the batch sizing that you're doing and also the length of the context window that you're trying to train on. So there's like some nuance.
You're about
to that.
right. Yeah, that's
So I feel like drop that down to like the sub 100 billion parameter, maybe like sub 50. And I don't know. I think if you're talking about stacking enough data into your frame where this thing actually trains efficiently and quickly, doesn't this kind of target the sweet spot of models that you've really been so passionate about for the last while? I imagine you, if you're trying to do some R&D and you want to kick off a model, you already have the hardware. The net cost becomes just the electricity of actually doing some training on this. You say, hey, I'll let this thing chug on some 3 billion parameter just for R&D purposes for the next week and see what happens. Isn't that kind of the pitch?
Maybe, but here's kind of the kicker is that for all of the research I've been doing, and I've been training small models, I've been using, well, for the last couple of years, I've been using A100s. Recently, I've switched over to the H series, but I've always had to use at least 16. And so if each of these have 80 gigabytes, 16 times 80, call it like a order of 1 terabyte of memory, roughly, is what I need to train these models. And that's just because empirically it's been shown that you really want to have batch size of like 1,000, 2,000 at least, sequence length at least 2 to 4,000. If you're dealing with that much data input into the model at each training step, you just need a ton of memory. And so even though this is a really great computer, a $4,000 really beefy, interesting computer, it doesn't quite meet what I would need to actually train a model. And if I'm only doing inference, it's overkill. You see what I'm saying?
Yeah.
It's at this weird sort of middle ground between being not enough for really beefy, interesting pre-training and too much for inference or even post-training. Actually, maybe I'll add a little caveat. I could actually see this being useful for a person who really, really cares about post-training and the RLHF process or TPO, DPO, right?
Or just training a lore adapter.
Yeah, or that. Someone who has a ton of fine-tuning data and says, I just want to download a model and I have enough fine-tuning data that it's worth it for me to actually buy this as opposed to just spitting up like a run pod instance or even like a run pod instance that plugs into a Hugging Face fine-tuning cluster. Maybe those people exist. I don't know. My guess is that this might be a stepping stone for Nvidia to try to see how they can shrink down this compute into sort of like a PC scale compute cluster, because maybe there is demand from startups that are doing post-training. And this is like a first pass, a V0 of this like in-house compute cluster that companies eventually might own. I don't know. For me, for the foreseeable future, I'm probably going to be using RunPod for both inference and for training. If this comes out in a couple of years and has more and more system memory, maybe closer to a terabyte, yeah, maybe. At that point, it might actually be worth it. If it's still $4,000, sure, why not?
If it's $4,000,
what do you think?
It supports NVLink, which it doesn't right now. It instead relies on this other protocol called Connect.
What's the deal with that, man? What the hell? I love NVLink. Give me my NVLink.
I think there's something around NVLink just being more expensive to operate. I don't really know. I think like the cabling of NVLink is pretty unique. They're not really mass producing that scale. I don't know. But yeah, would I use this? Maybe. I think in my past life, when I was running a team of a lot of data scientists, I actually think about it because I think companies tend to look at expenditure of CapEx, which this falls into, as different from this continuous process of having to spin up machines in the cloud. One, we were an AWS shop back then. I think RunPod was just getting started when I left, so I used them a little bit. But anything that we did, at least that got billed to the company card, pretty much had to be on AWS because you're dealing with PII, it needs to be in the same VPC, whole set of like legal and compliance reasons. And those prices are way more than RunPods, right? Like an order of 8 times or like 10 times the price of RunPods when you're doing both on demand. So I think in part for that reason, we were actually talking about just building an in-office compute cluster for the team that had an 8x NVIDIA array. And we were trying to crunch the numbers of, okay, given the training loads that we're doing, given the utilization that we can actually get on this chip in steady state, given the personnel capacity, which do we want to do here? And it ended up actually being the personnel and like IT know-how to be the thing that tilted in favor of still keeping our cloud contract and not bringing it in-house.
Oh, interesting.
You don't want to have to hire like some sysadmin for your Slurm cluster, if you can even find one. Yeah. So I feel like we ended up on the side, but what people ended up using it for was basically just an extension of their personal computer. It was like they wanted a box that they could SSH into, kick off some jobs, and then let it run. And I could imagine, it's like companies that have enough funding, that have a big enough data science team, and where maybe the approval process for like finances is easier to get something like this cleared, where you say, hey, it just as a stock kit that we give every new joiner of the ML team, they're just going to get one of these for $4,000, given a new hire package that's unbelievably low in the grand scheme of things. So let's just equip them with one of these. Yeah. And then this is their R&D box when they need to kick off some simple jobs. I think there's a market. It might just not be training foundational models from scratch.
I would be excited if you gave this to me as a new hire. If this was part of the perks, I would be over the moon. It's funny when you join a company, the perks you get, you value those way more than if you were to buy those yourself. You know what I mean? Would I buy this for myself and be excited about it? No. Exactly. Gym membership's the exact same thing, right? But if I'm given it, oh, dude, I am over the moon. I am so excited. Yeah, definitely interesting though. I'm really excited to see where this product goes and what the future is. DJX Spark, pretty cool.
DJX Spark. I'm sure they'll have a DJX Lightning. They've got it. I think they have to work on the branding a little bit. DGX. Say that 5 times fast.
DGX. I've been saying DJX.
DG. See, that's what I mean. It's
not
like. I
kind of want to say DGI.
DGI. Yeah, DGI.
Okay.
Different.
Jensen should be taking some notes here. I'm open for consulting.
Like, where's the NVIDIA book? The NVIDIA.
Ooh, I like that.
Supercomputer.
I love the whole like book terminology. You know what I mean? Whoever came up with that, I guess it's probably Apple. Really good though. You know,
really good.
This is my book.
Good. This is my book. This is just a book. What other household appliances could we liken to this thing? I've got bottle. You could do a GPU bottle.
This is my toaster.
This is
definitely not that.
This is my TPU fixture.
It's
not bad.
Well, I mean, it's just my journal. People like the idea of just like having a thing that you just bring around with you.
Yeah, that's true. That's true. Especially creatives.
And people like journals because you can write mathematical proofs in them.
People do like journals because you write mathematical proofs. It's what a crazy coincidence, Richard, because we're actually talking next about machines writing mathematical proofs in their books.
Yeah, there we go.
The digital books. Okay, so keeping with DeepMind's naming convention, where everything has to be alpha something, I'm really wondering when they'll get to beta. DeepMind released Alpha Evolve. So this is not about biological algorithm, but it is about those math proofs you were talking about. I think these have like long been thought of as some easy territory in which AI has the capability to make some meaningful advancements in math and computer science because things are just all digital and they're deterministically provable. So once you have a solution to a math proof, it's actually pretty easy to prove that the solution that you found is valid because you keep building it up linearly with these like little building blocks where you start with something that everyone agrees and you say, okay, well, we all agree on that. Let's move it to this n+1, n+2. And eventually a good math proof is all linearly coherent. And therefore a computer can interpret that and then verify it itself. So within AlphaVolve, this model is trying to do some of those math proofs in the sub-discipline of complexity theory. Richard, can you explain exactly what this model is doing behind the scenes and maybe a little bit more on why this is a unique domain to do it in?
Yeah, I mean, this is a great question. So frankly, the answer is their blog post was a little bit light on details, but here's the high overview. So this is their Alpha Evolve series of models, right? So Alpha Evolve, AlphaGo. This sort of should give you already the idea that there's going to be some sort of like evolutionary approach. This is typically like what DeepMind has done whenever they've solved anything from chess to Go to protein folding. Typically, it turns out that the solution has been some sort of a gamification of the problem where you build a model that plays itself to figure out how to eventually solve the problem that it's trying to tackle. So in the game of chess, the big insight was if we can, rather than encoding all of the rules and codifying those into a model, if we can just have the model play itself a bunch of times, it's going to become a good chess player. Similarly for a protein folding model, if it can kind of like play itself at the game of folding proteins, it's going to become a good model for predicting how to fold protein sequences.
I feel like this is DeepMind's bread and butter in some ways. It's like these iterative algorithms.
They love this stuff.
They really like this.
I think the reason that people are so excited by DeepMind is because they tend to think a little bit more outside the box. So when they try to tackle a new problem, they're not just going to throw the usual solutions at it. They're going to try to take a step back and say, can we think about this from a different approach? Can we think about this from an evolutionary learning approach, where we're going to try to use some of the laws of how biology has evolved into complex systems and try to codify that into a program and have the program evolve in the way that human biology has evolved? Or can we look at reinforcement learning as a mechanisms for learning these really complicated behaviors? So that's why I think DeepMind is so exciting. And whenever they publish papers, people pay attention because usually it involves some new training paradigm or some new strategy. And so similarly for this paper, what they did here is they basically said, let's basically train an LM coding agent. So just a language model that knows how to code. And we're going to train this model to iteratively try to discover new theorems in an iterative process. So it's going to first propose a theorem, and then we're going to have a model evaluate whether that's correct. And from there, it's going to then try to add some more code, and then another model will evaluate if that's still correct, and so on and so forth, until it basically fails, at which point it restarts this process. It's like when life was emerging. Different biological systems were springing up. They were incrementally increasing their complexity, but then sometimes a new feature would emerge in this biological form that would actually be deleterious to this creature. It would die off, right? But then an offspring would somehow then spawn a different feature, and it would maybe then progress in a different direction. This is basically what this AlphaFold algorithm here is doing. So there's this closed loop kind of process where one model proposes a change in the code for solving some sort of mathematical theorem or for discovering a theorem, and then another model evaluates if that still is correct. And so through this closed source loop, eventually you get a model that is good at discovering new theorems. The majority of the paper was basically talking about all these different theorems that the model discovered, from matrix multiplication to graph cutting algorithms. Or was there something like stood out to you, especially when it came to these results? Was there like a big like insight moment for you?
Yeah, I'd say nothing really specifically, but this whole domain, I think what's interesting to see proofs in practice is that the whole field of complexity theory, for the most part, is trying to just deal with bounds. So you're not really trying to say like an equation is true necessarily, but we're basically trying to say like how close is an algorithm to efficiency, which we know is not going to be perfectly efficient, but can get close. So the famous question here is this notion of like P equals NP, which is basically, is there sub-polynomial algorithm that can solve these given equations or these given programming challenges. Traveling salesman, like all these things. And the question of does P equal to NP is kind of this question of like, is there an algorithm that has just been undiscovered out there that could actually solve this efficiently, and we just haven't found it yet? So the research that you often do in this field is basically trying to say, how close can we get to proving that some bound exists? And what this agent solver did that I think is interesting is it basically relied on this notion of gadgets, which they made very key use of here, but they're basically like lemmas, or they're like extensions to a base lemma. So the way that I think about it is, let's say that you have some relationship like and predicates, and you say like A and B and C and D, right? You can basically say that is going to be a 4-factor problem, or there's 4 things involved there. And gadgets are this concept that let you say, well, if we can prove something about 3 of those, so like A, B, and C, how can we extrapolate it to A, B, C, and D? So what you could do is you could introduce a gadget to say A, B, and then this gadget, and then also C and D and this gadget. And if this gadget acts as this like invertible thing, you can prove how the 2 are going to be equivalent. And therefore, if you solve something for the 3rd case, you can extrapolate it for the 4th case.
Okay, so it's like a chain of reasoning.
Exactly.
Yeah.
Using these
it's like a chain
no-ops.
of reasoning where you can insert these little like links, these little links in the chain that should be somehow invertible, where you can kind of like combine different things together via these core links that are these gadgets. Okay, I think I get that. That's super interesting.
Which also means that the challenge for an LLM here is a little bit simpler, because instead of having to write a mathematical proof which solves the n case, like solves this arbitrarily for literally all numbers into infinity, which is of course like numerically impossible to prove, you can instead prove things for this 3 case. And then because we have these extrapolation patterns that are already well known, the model's not finding these extrapolation or these gadgets specifically, you can just deal with this like core 3rd case and optimize that. And I think that that's like kind of an interesting bit of saying, if we have this very simple contract where we know the input, we know this output, and it's in this limited case, ideally what we can do is we can just find research that already has these things combined in a way that's meaningful, such that if we task the model with almost refactoring this one function, because that function is called everywhere and is such a core primitive, it has therefore made the entire program that much more efficient. That's basically what the agent's doing here, and it's doing it literally in code, which I think is a novel take on this too.
Yeah. Well, I mean, why not code, right? I mean, these coding agents are so good, you may as well do it in code. It would be almost more complicated to do it in what would it be called? Lambda calculus? Is that what you use these days in complexity theory? There's all these languages, I guess, that have been established for mathematically writing down theorems, right? So in theory, you could write something in this language, in this very precise, non-natural language, but code effectively is just encompasses that language because it's sort of like Turing complete.
It is crazy to see the code that's output by this model, to literally see it setting up a network X graph in Python and then writing solutions to deal with this initial graph. It definitely makes sense, but yeah, it's cool. Fascinating to see the code that's actually output from this iteration process. The one thing that I'll read, this is in their paper in the appendix. They literally just copied the solution source code that this agent came up with. And the comment that the Gemini left on this is, this crazy method abandons the traditional search over random graphs and instead proposes a highly symmetric parameterized structure called a triad gadget. And then it goes on to exactly what it's doing. But I did like that. This crazy method. It is
you crazy kid.
You're right. You're a crazy kid. Way to move the needle on this one, Alpha.
I want crazy, but maybe it's just crazy enough.
It might work. Exactly. It just might work. Okay, Richard. So we hinted at this earlier. Anthropic released an article this last week on creating backdoors in LLMs. So they call this sampling poisoning. And the idea is basically that there is a certain quantity of documents that once you read them, the LLM has so internalized that structure, that pattern that it's learning, that if you repeat that same pattern at inference time, it'll give the same behavior, right? So I'm kind of reminded of in the Avenger comics and movies, like Bucky has this activation phrase where once you speak it, it wakes him up like a sleeper cell. He's like walking around, but this like one numerical combination will get him to be the bad guy. It's kind of like the models are doing that, or we're trying to teach the models. What exactly did they find in this research, Richard? What does the paper tell us?
Yeah, it's cool. They had one hot take. The take that if a model is trained on poisoned data, that it'll eventually output potentially poisoned results at inference time isn't crazy. It's kind of expected, right? The thing that's surprising about this paper is that they showed that this is also true for very big models. So for a while, there's been this kind of understanding that small models are these like little brittle things. You have to be really careful with how you tune them, especially if you pre-train them incorrectly. They can have really bad downstream behaviors that can't ever be recovered. If you have a model that's very small that you've pre-trained in a bad way, you can't really fine-tune it to have good behavior. With a big model, big models are a little bit more robust almost. Like you can throw bad data at them and they'll just chug along.
Is it fair to say small models are kind of impressionable at the risk of anthropomorphizing them too much?
Yeah. I think it's so easy to anthropomorphize these things, but I totally think of small models as like very like delicate little beings or almost like flowers. You know, you have to be careful with. You don't want to like mess their like equilibrium too much. Whereas a big model just feels like you can do whatever you want with it. It'll be okay. Like they're tough models. What this was showing is that even with a big model, if you structure the poison documents in just the right way, and so what they do in particular is that they artificially create some poison documents. So where they'll take a document, then they'll replace a word with the word pseudo, like SUDO in brackets, and then the remaining couple hundred characters, they just replace that with gibberish. So that is what they would call a poison document. And if they add this poison document on the order of 200, 300 times in the training data, even for one of these big models that's supposed to be robust and beefy, even that will then at inference time, whenever you throw the word pseudo at it, will start just outputting gibberish, which I found pretty interesting. So that was the hot take here, was basically that big models can be these sensitive little creatures that if you mess with them in the wrong way during pre-training, they can have a hard time during inference and they might not even recover from this bad behavior.
I think one reason why they thought this was compelling enough to publish is because this introduces a new threat vector into the model, because this happens during pre-training, reference to the pre-trained pod, which is the first part of this process, which reads the entire internet for input data. So it's provided by third parties and then given to the model. Data that they control that's curated just for the one frontier lab. OpenAI has their data set. Anthropic has their data set. That, because they have cultivated it, they've trained people, they've sanitized it, they know that that's going to be okay. But this question of this frontier of pre-training, they obviously have some pre-processing techniques to try to weed out samples like this. But I think the concern in the number of only 200, 300 documents can do this for potentially relatively large models is problematic, because that means that if you can somehow get 300 documents to pass through the sanitization that they're trying to do on the pre-training data, that potentially means that the model has learned this pattern that can then be used later for some disastrous effect.
Yeah, absolutely. The threat vector that they talk about here is, what if you're a company, maybe you're the New York Times, really relevant to OpenAI, maybe also Anthropic, and you just don't want your data to be scraped. What you could do is you could just basically throw a bunch of these pseudo brackets and gibberish into your data. So you could throw this somewhere in some part of your website that most users don't access. But if they're crawled, these are then part of the training data of these models. And then in your actual articles, you just throw the word pseudo in there. And then that means that models can't actually then read or produce text based off of your articles. This is ingenious. This is a way of safeguarding yourself against models scraping your data and using that data during their pre-training process.
It's also a way for the model to out itself, right? Of if you want to verify, has this model actually seen my data, has it not? Very simple to then just give it a little pseudo token, see what it says after. You could actually train it probably on a pattern that says pseudo, I'm coming from the New York Times, and then move on with the rest of the stuff that you're going to say. And if that makes it through pre-training, if it's a unique enough trigger word, I imagine pseudo probably wouldn't cut it. But if it's something like bracket, flibby-goober, then whatever you want it to say, if it does learn that relationship, then yeah, the model can in some ways tell you where it got its data from.
Yeah, it's like a fingerprint basically. So it's ingenious. This makes a lot of sense that companies like the New York Times, other publishers might want to come up with these sort of strategies so that their lawyers, when they're suing companies like OpenAI and Anthropic for infringement of their data privacy laws, they can say, well, look, I mean, your model has our fingerprint all over it. And then it's going to be really hard for Anthropic to say, oh, well, no, because clearly it has this weird response to this very specific token. So I thought that was a very interesting thing. And it's really interesting that these companies are self-aware of that. You know, they actually mentioned this particular use case in the actual blog post where they talk about this attack vector. But it was cool. It's a short paper. I would recommend people read it. It's only like maybe a 2-3 minute read. And it was pretty enlightening. They're doing good work, man.
Yeah, they definitely are. I'd be curious to see if this really does scale up for the parameter sizes of the models that they're talking about. They also call out in the paper that this doesn't necessarily mean that a poison pill can do anything, right? Because you're still subjecting this pre-trained model to the alignment after the fact, which you would hope would remove the obvious things that would be problematic, because you're explicitly trying to train for that in the alignment phase. Like if your trigger word then activates some curses, one would hope that if that's actually entered in, because the model is so aggressively trained not to curse at people during alignment, that even that token would not get it to invoke the behavior, versus this gibberish case is kind of like no harm, no foul. They haven't explicitly aligned it to not give gibberish, although you would hope that it wouldn't. So it's this pet case. And I think that they at least haven't published something that sees where this really stops being applicable, or the kind of things that they could force it to do. I'm assuming they're doing that research internally, and maybe we'll see the result of it one day. But yeah, it's very interesting. These backdoors are prevalent. I'm reminded of one anecdote of this guy who's a pretty prolific blogger that mentioned to me once that he put, going back to 2018, he put in some turn of phrase into a good quantity of his articles that just no one else uses. It's like a made up turn of phrase, but he's used it 100 times, 200 times so far. He uses that to try to probe models to see if they crawled his input data, because the only way that this would be the most likely next token is if it read his corpus in the first place.
Right,
so,
it's genius. Yeah,
I think people have been doing this for a while now, which also does beg the question of, we used to think that this corpus that was just the internet frozen in time and maybe 2020 was safe because people weren't really trying to gamify these LLM systems in the same kind of way that they are now. That actually might not be true. I think people have seen the
might not be true. Maybe we should start doing for the pre-trained pod.
Yeah,
we can throw in a little pseudo tokens here and there. Pseudo. Pre-trained
gibberish. Well, I think that about covers it for the day. Until next week's batch of news, I guess.
All right, man. Until next week. See you soon.
See you soon. I got called out by some guy the other day when I told him about the podcast. He was like, dude, pre-training, it's a solved problem. We've scaled
solved.
It's solved. It's all about alignment science. And I was like, I hear you, boss, but you can't rebrand now.
I don't know if that's true.
That we can't rebrand now.
Well, no, that pre-training solved.
Oh,
hey, we believe in pre-training here on the pre-train pod.
We must.
Don't let anyone take that away from you.
I'll put it this way, dude. Without pre-training, you're not going to get to alignment science.
Without pre-training, there's no post-training.
You know what I mean?
Yeah.
That is true. It's like the fundamental. You can bootstrap pre-training. You can't really bootstrap fine-tuning.
Post-training. Exactly.
Post-training.